Good evening, everyone.
Good evening,
Good evening,
sir.
sir.
So I'm sharing my screen.
We got the drive link for the notes, sir.
You got it? Okay, good. And also, you must have got the link to the videos as well. It's actually shared with all of you.
Yes, sir, we have it, sir.
23 batch. Correct?
Yes, sir, 23 batch.
Yeah, 24 batch anyway has the access through the portal that you are saying. Yeah? Okay. Good. So let's get started. Yeah. You're able to see my mouse, right? My pointer.
Yes, sir.
Yes, sir. Yes, sir. We
Good.
can see, sir.
Okay, let's get started. So until now, we have looked at structure of the material, and we have realized that in a crystalline material, one can have defects, and different kinds of defects can be there. And we've looked at point defects and line defects. And we also understood the mechanism of plastic deformation. How plastic deformation takes place, what is the underlying atomic scale mechanism that is responsible for plastic deformation, which is nothing but dislocation. Right? And we have looked at what happens in a single crystal and what happens in a polycrystalline material. And many times in engineering, we will deal with a large fraction of our work deals with polycrystalline materials. And we need to measure these mechanical properties of these materials in order to be able to design components. So in this module, what we are going to look at is the mechanical measurement of mechanical properties from the perspective of uniaxial tension test, and how we can use uniaxial tension test to measure certain properties which will be useful for design of components. Okay. So we will look at how a uniaxial tension test is done. I'm sure all of you would have gone through the uniaxial tension test in your undergrad course, but we will try to refresh, and then we'll try to understand the stress strain curve that we would see from a uniaxial tension test in a little bit more detail. And then looking at the stress strain curve, we will try to deduce some properties that can be obtained directly from the stress strain curve. And then we will, having learned about the mechanism for plastic deformation, how that underlying mechanism manifests into a stress strain response that you would see macroscopically. This is something that we are going to discuss. So let's first understand what do we mean by plastic deformation. When we are looking at plastic deformation, in the plastic deformation range, we will try to understand the onset of yielding and try to measure the property called yield strength of the material. Then we will look at the tensile strength. And in this context, we will talk about the concept of necking just before fracture in a ductile material, which can be explained through a mathematical model given by Consider. And we will discuss about something called a Consider criterion. And then we will discuss what do you mean by ductility, resilience, toughness, and all those things. Okay? Okay. So in this module, our objective is to be able to define what is an engineering stress and engineering strain, what is true stress and what is true strain. And we will state Hooke's law and its limitations. And we will define a very important property called Poisson's ratio. And if you are given an engineering stress strain curve, if you do an experiment and get an engineering stress strain curve, will you be able to measure from the stress strength of data, what is the modulus of elasticity, which is nothing but elastic modulus or Young's modulus of elasticity. Will you be able to estimate what the yield strength is, what the tensile strength is, what is the percentage of elongation before flexure? So these are the properties that you would estimate given a stress strain curve, right? That is what we are going to learn. And not only that, we will discuss the microscopic details of the deformation and the failure by using a model system such as mild steel under uniaxial tension test. And another thing that we will try to learn is if you are given dimensions of a specimen before and after the test, we should be able to plot the true stress strain curve from the engineering stress strain curve. So we will discuss these things in this class. Okay. So before we move forward, let me refresh your memory about the concept of stress. Okay. We all learned stress in our undergrad classes as a quantity defined as force per unit area. Right? I will live with that definition as far as this class is concerned, but otherwise in a different class, stress is defined in a more generic fashion. But as far as this class is concerned, we will live with the definition of stress as a force per unit area. For example, if you take a three-dimensional body, which is subjected to various forces P1, P2, P3, P4, P5. And now let us look at a point O. And if you cut at this body, right, this is MN plane, MM plane, if you are cutting, then you will have the force acting, internal forcing acting on that body, and that you are talking about a point O. The stress at point O on this plane MM, assuming that a force delta P, a small force delta P is acting on a very small area delta A. So assume an infinitesimal area around that point. Then the stress, which is in this case normal stress, is defined as limit delta A tends to 0, delta P by delta A. That is the definition of stress. And here the stress will be in the direction of delta P, and usually it is inclined at an angle to delta A. When I say delta A, I am talking about an area. And when we are talking about area is not a scalar, it is a vector, meaning to that surface, that infinitesimal area is what we are looking at. And we are talking about area when we are discussing, we should mention the magnitude of the cross-sectional area and the normal to the surface. So that is why area is a vector. That is why usually this delta P is inclined at an angle theta from the area. And that results in the components called normal stress and shear stress. Okay. So if it is oriented at an angle theta, so then the normal stress is P by A cos theta, and the shear stress can be written as P by A sin theta. And again, the shear stress within the plane can have two components along x and y direction. And those components, if that within that plane, if it is at an angle effective with respect to x and y axis, it is at an angle phi, then we can write shear stress components tau along x direction, along y direction will be P by A sin theta sin phi, P by A sin theta cos phi. This P by A sin theta is a resultant shear stress acting on along OP here. Okay. So this is how we define a normal stress and shear stress. So if you are given a plane, hence a given plane may have one normal and two shear components of stress in general. Initially we said stress is force per unit area, but because the force is not necessarily in the direction of the normal to the surface, which in general it is inclined at an angle to the normal to the surface, then let us say this angle with the normal to the surface is theta, right? And then that angle, Z is your normal to the surface, and then normal stress is P by A cos theta, and shear stress will be P by A sin theta, right? And P by A sin theta is along this line, and P by A cos theta is along this line, and P by A sin theta is now in the plane, that is this guy is oriented at an angle phi with respect to y axis. So along y, it will be P by A sin theta cos phi. That is why along y, P by A sin theta cos phi. along x, p by a sin theta sin phi. I hope you are able to see how we have written these things. So, in a given, if you are talking about a plane, on a given plane, you will have three components of stress. One is normal component and two shear components. Is that clear? Yeah?
Yes, Professor.
Yes, sir.
Yes, yes. If that is clear, then we will move on. And now we will go to start defining another important quantity called strain. As we have learnt in our undergrad classes, average strain or engineering strain is given by change in length, that is delta, divided by original length L naught. So delta is change in length, that is delta L. This is the displacement by L naught, where displacement is given by delta L, that is initial length, final length minus initial length divided by initial length. That is your engineering strain. So change in length over original length is your engineering strain. Whereas true strain is defined as change in length per the current length. If you define this guy over an initial length, that is L naught, but if you define it over a current length, that becomes a true strain, which is also called natural strain. And usually it is defined as d epsilon is equal to dl by L, because the current length, then you can only talk about infinitesimal strain. But if you want to calculate total strain, you have to start from L0 to LF. So integrate L0 to LF, dl by dl. L, that will give you natural log final length by initial length. That will be your true strain. So one can always write a relationship. So L is like LF here. So LF minus L naught by L naught. So I can write LF by L naught minus 1, right? So LF by L naught is equal to 1 plus E. E is engineering strain. So I can replace this LF by L naught as 1 plus E. Are you able to see that? Is there any? I am saying that true strain epsilon is equal to natural log LF by L naught. LF is final length. So in this equation, when you are defining engineering strain, L will be the final length minus initial length, right? I could write L as LF minus L naught. So LF minus L naught by L naught is LF by L naught minus 1. So LF by L naught is equal to 1 plus E, right? So LF by L naught is 1 plus engineering strain. So in this equation for true strain, epsilon is equal to natural log LF by L naught can be replaced by 1 plus E. That is how the true strain and engineering strain are related.
Sir, can we say this true strain as an instantaneous strain at that point?
D epsilon. So the way that we need to define a true strain is D epsilon. That means instantaneous strain is DL by L. But if you are, so it is like this. Let me write it down for you. Let me take my iPad and then write it down so that it becomes clear. Okay. You are able to see my screen, right?
Yes, sir.
Yes.
So what I have said was my engineering strain E is equal to change in length by original length. Change in length is final length minus original length by original length. That is equal to LF by L naught minus 1. Right? So my engineering strain, I am calling it as engineering strain E is equal to LF by L naught minus 1. That implies 1 plus E is equal to LF by L naught. All of you agree with that? Now, the true strain, that is d epsilon. That means if you take a bar and if you are straining it, then it will become at time t equal to 0, it is this, t equal to 1, it is this, t equal to 2, it will become like this, right? So instantaneously within this time, the strain d epsilon, infinitesimal strain, is equal to change in length dl by current length, right? That is the definition of true strain. So now this y, it has become from here to, this is L0 and it has become to LF. So what should I write? So the total true strain epsilon is equal to integral L0 to LF dl by L. All of you agree with that? Because this is incremental and total true strain is this. So 1 by L integral 1 by x dx is what? Natural log x, right? So that is what I am doing. So true strain is equal to natural log L between limits L0 and LF. If I apply that, then epsilon is equal to natural log LF by L0. Now we have just now seen LF by L0 is equal to 1 plus epsilon. Therefore, true strain epsilon is equal to natural log 1 plus, sorry. Right? This is engineering strain. Is that clear? Yeah?
Yes, sir.
Any more questions on this? Okay. So now let's go back to our so now the shear strain in a body is basically shear strain is talking about rotational part. So let us say this red square is your initial body and it is sheared by a shear application of shear stress. Then this vertical line will change its angle to theta. So shear strain gamma is equal to A by H, which is tan theta. For a very small values of theta, tan theta will become equal to theta. So that way, that is how you will represent shear strain. Okay. So now we have defined what is the normal strain, what is the normal stress, shear stress, engineering strain. But of course, we have not defined what is engineering stress, right? What is engineering stress? So, did we define engineering stress or not? We will talk about it at a later time when it comes. So let me continue. So engineering strain is change in length for original length. Engineering stress is nothing but force per unit area. So we will say force per unit original cross-sectional area is engineering stress. Force per unit current cross-sectional area is called true stress. That is the only difference. Okay. So now in order to measure the properties that we have talked about, we can use various tests. For example, one of the popular ones is uniaxial tension test. In some branches of engineering, such as civil engineering, they use compression test. Most of the times because the materials are primarily loaded under compression. So when you are trying to design a column, for example, columns are usually designed for resisting compression. If the materials strength in tension and compression are different, then it does not make sense to do a tensile test, but you have to do a compression test. That is why compression test is also done. And there is also shear test and torsion test. So these are all the various tests that people do in order to measure mechanical properties. And in this class, we will mainly focus on the tension test. Okay. So this is a very popular test, uniaxial tension test, is very well known across community. Mechanical engineers are definitely very much familiar with this test. And there is a standard that is generated, that is developed by American Society for Testing of Materials. The standard is called E8. The ASTM E8 standard is for conducting uniaxial tension test for metals. Okay. And there are different kinds of specimens that one can make it. This is one cylindrical specimen. Sometimes you can also have a flat specimen. And this is what we call a dog bone type specimen, which is having a cylindrical cross section. Sometimes you can also have dog bone specimen with a flat cross section, rectangular cross section. Here we are seeing a cylindrical cross section specimen. And these are standard dimensions. So one needs to, whenever you want to do a tension test, you have to do the tension test using these specimen dimensions around the world, so that all of us are using the same kind of geometry in order to report the results. And that this is a typical configuration of a uniaxial tension test, uniaxial testing machine, universal testing machine, not uniaxial, universal testing machine. It is called universal testing machine because it allows us to do tension test, compression test, torsion test, depending upon the fixture that you add. The frame will look very the same. And here you have grippers. Between the grippers, you have the specimen, and then you increase the gap between. Here you have a load cell which will measure the applied load, and this is a moving crosshead. As you move the crosshead, then there will be deformation in the specimen, which will be measured using an extensometer, and the load resisting load is measured by the load cell. And here you have a screw type this thing. So you have a motor which will rotate the screw. As a result, the crosshead will move down or up, as the case may be. So when you do this test, you put a specimen, metal specimen like that. Then when you apply the load and then you measure the load, you can only measure load. And this is the what we call gauge section, where you have a gauge length and gauge diameter is something. And you will measure a load and displacement. That is all you will measure in a uniaxial tension test. But that load and displacement data has to be converted to stress strain data. Here we are talking about engineering stress versus engineering strain. What do we mean by engineering strength? Change in length for original length. What is that original length that we are talking about? We are talking about the original gauge length. So the extensometer is placed between these 2 points, and as the specimen is deformed, the extensometer records the change in length, right? And that change in length divided by original length, which is actually known to us, will come on to the x-axis. And the y-axis, you have to plot stress. What is that we are measuring? Through the load cell, we are only measuring the load, right? For corresponding each change in displacement, we are measuring the load, but that load divided by the gauge section cross-sectional area. This cross-sectional area is what is written as engineering stress. And the cross-sectional area, as the material is deforming, the cross-sectional area changes. But if you use the original cross-sectional area, that means the cross-sectional area corresponding to 0.505 inches, 5/4, 0.505 whole square will be a certain cross-sectional area. That cross-sectional area, if you use to divide with the load applied, then that becomes your engineering stress. And now if you look at that graph, in the initial regime, you will have a straight line. If you are doing it, for example, if you are using it with mild steel, you will see a straight line. What is the meaning of that? So most of the steels, it will show metals, it will show a straight line, which basically means that it will have a constant slope. And the slope of that line is what we call elastic modulus. So the slope of the linear segment is called elastic modulus or modulus of elasticity. And during this process, suppose if you are loading the specimen, that means if you are deforming the specimen, let us say you have deformed up to this particular strain, that means corresponding to that, you will have some stress. And again, if you unload, the unloading data will also follow the same path. That is why this is what we call elastic regime. Okay? The elastic reformation, if you remove the load, then it will go back to zero stress. That means the load becomes zero, then the strain also becomes zero. when you are unloading along this path. As a result, you will have a pure elastic deformation. That is what we call pure elastic deformation. And there, here you can clearly see that stress is proportional to strain. Not only that, it is directly proportional to strain. That means it is a linear relationship, and the proportionality constant is your elastic modulus. So that E is the slope of this line, sigma is equal to E epsilon. This is what we call Hooke's law for a linear elastic material. What do you mean by linear elastic material? The line is linear, and as a result, the slope is constant. So elastic modulus is a constant. It does not change with respect to strain. That is what we mean by a linear elastic material. If it material is non-linear elastic, this curve will not be straight line, but it could be some curve like that. Then the slope of the curve will be changing as a function of time. Then we will not call it as elastic modulus, but it will be called as tangent modulus, which depends on the local strain, and then the elastic modulus is a function of strain. So elastic modulus will not be a constant anymore. That is the case with nonlinear elastic materials. Okay. So this is how a nonlinear elastic material looks like. For few materials exhibit such nonlinear elastic response. For example, gray cast iron, polymers, concrete, and so on. So the modulus is not straightforward. There are two ways at each and every point. Suppose if you are measuring elastic modulus at sigma 1, you can draw a tangent here, and the slope of the tangent can be reported as a modulus at that particular stress or that particular strain. Or there is another way, there is something called secant modulus. If you are looking at sigma 1, you will draw a line between origin and the sigma 1. The slope of that line is called secant modulus. If you want to report slope secant modulus at sigma 2, you draw a line from here to sigma 2, and then that slope will be called secant modulus at sigma 2. So as you can see that the slope will be changing at which point you are measuring. That is why it is called a nonlinear elastic material. It is still called elastic because when you remove the load at any point, it will come back on the same path. And when you make the load zero, the strain also will become zero. That means material is coming back to its original configuration. That is why it is still called elastic. Any questions here?
It's clear, sir.
Yeah. Now, so how do we understand this elastic deformation? This elastic deformation is nothing but in the material, you have atoms and you are applying the load. What is happening is the atomic bonds are stretching. They are only just stretching, but they are not breaking, right? So this elastic deformation represents a small change in interatomic spacing and stretching of interatomic bonds. So if your force is an interatomic force as a function of distance between the atoms is given by this, depending upon the material, you will have different graphs. If you look at this red color graph, this is the property of a material, which sort of gives us the elastic modulus when at a zero, this is what we call equilibrium separation distance, at which the force will be zero. At that point, if you take a slope of this line, that represents our elastic modulus. The elastic modulus will be directly proportional to that. And you can see that if this is for this kind of a material, the material elastic stiffness will be higher compared to this kind of. This is weakly bonded. That means elastic stiffness will be lower here. You can see that, right? So the magnitude of elastic modulus that we are measuring here, whatever we are measuring here, is a culmination of the interaction between the interatomic bonds, right? So measure of resistance to separation of adjacent atoms. Because when you are applying the load, you are actually stretching the bond. What is the resistance that is offered by that bond is perceived as elastic modulus when we are measuring macroscopically. All right. That's about elastic deformation. And now we'll talk about inelasticity. What do we mean by inelasticity? If you look at the elastic deformation, there is no time that is coming into picture. It does not depend whether I am loading it faster or slower. Elastic deformation does not depend on time. Whereas, if in some cases the elastic deformation depends on the time, so you will have time dependent elastic strain. What is the meaning of that? So the meaning of that is that elastic deformation continues after the stress application. What do you mean by that? For example, in this particular picture, if you are applying certain stress, then I know my strain is so much. That means that is my elastic strain. That is the deformation. And after I am applying the load, I will have instantaneously that much strain. You will get that strain instantaneously. But if the strain continues after applying the load, you have instantaneously some strain. Even after that, it further continues to deform as a function of time, although you are not changing the stress. That means the strain up to here, if you apply the stress, suddenly the material will have this much strain, and then it will continue to increase the strain without change in stress. That is what we, as a function of time. Okay. Then such deformation is called inelastic deformation. So elastic deformation continues even after the stress application. And once you release the load, here, pure elastic deformation, if I remove the load, as soon as I remove the load, the strain becomes zero instantaneously. There is no time lag. That is what a pure elastic deformation is. Whereas if we are dealing with an inelastic deformation, upon release of the load, you actually require some time for a complete recovery. Right? So this is what we call a time-dependent atomistic process. For metals, it is not very significant, but for polymers, we will have the magnitude of the elastic component significant, and the materials, polymers are referred to as viscoelastic materials because there is some viscous effect. There is a time-dependent deformation. Okay. So we have discussed elastic deformation, and we have discussed modulus of elasticity or secant modulus. Now we will define another important property called Poisson's ratio. So when you are applying a load, let us say in one direction, okay, when you have applied, so initially the body is the dashed line, the blue color one, and then it is applied with a stress of sigma z, then the body gets elongated in that z direction. And as a result, laterally it will contract. You can see that, right? There is a lateral contraction in the body, which means if you, the material is isotropic, the lateral contraction in the x direction as well as y direction. This is x direction and that is y direction. The lateral contraction will be same for an isotropic material. Now, you will see that suppose if you are pulling the body in that direction, the strain will be positive in the direction of the application of the load, isn't it? Because it is tensile strain, that means change in length is more than the original length. But if you look at the lateral direction, the original length was this much and the final length has got reduced. So the lateral strain is negative, isn't it? So now the Poisson's ratio is defined as negative of lateral strain divided by the longitudinal strain. Because it is an isotropic material, epsilon x and epsilon y will be same for a given epsilon z, right? So Poisson's ratio is equal to negative of epsilon x by epsilon z. We know if epsilon z is positive, then epsilon x will be negative. If epsilon z is negative, then epsilon x will be positive. As a result, epsilon x by epsilon z will always be negative. That negative number multiplied with a negative symbol will always be positive. So your Poisson's ratio will, if the way that you have defined minus lateral strain by longitudinal strain, it is defined this way in order to report that as a positive number. Theoretically, one can have, for an isotropic material, you can have a Poisson's ratio going from 0.25 to 0.5. But for most of the metals, you will have 0.25 to 0.35. Now, with recent advancement in materials, you know, whenever you are pulling a material in longitudinal direction, lateral direction, what should happen? There should be contraction in the lateral direction, right? But now we have a new class of materials called auxetic materials. These behave very differently. If you are having a longitudinal strain, tangential longitude, if you have a positive strain in the longitudinal direction, normally lateral direction you will have compressive strain or negative compressive strain, means the change in length, the original length will be negative. But These oxalate materials are a special class of materials. They will, if you are expanding in the longitudinal direction, in the lateral direction, instead of contracting, in the lateral direction, they also expand. That means they expand both longitudinally as well as laterally. If that is the case, both epsilon x and epsilon z are positive, and hence the Poisson's ratio will be negative. These are called metamaterials because they exhibit negative Poisson's ratio. These are a special class of materials that have several engineering applications. So metamaterials, these are called mechanical metamaterials because they give an unprecedented properties which are not otherwise possible by regular materials, because we don't understand what we mean negative Poisson's ratio, but these metamaterials can give us negative Poisson's ratio. This is called a mechanical metamaterial. But you also have something called an optical metamaterials. So here you are seeing one example of an optical metamaterial wherein you can see this guy is wearing a jacket and you can see through the fellow. The people who are walking on the other side behind him can be seen through this jacket. That means he sort of became invisible. If you play with the color of this jacket in such a way that this jacket can become invisible. Imagine this guy is wearing a similar thing like that. You will see his shape, but it is an invisible. And this is what we call optical cloaking. Right? Similarly, this is where you can see a material which has a negative refractive index. A normal refractive index will show something like that. If the material has a negative refractive index, you will see, although this is not a broken piece, okay? It is the same straw. Because of the refraction, you will see a change in angle inside the water. But if you have a material that has a negative refractive index, instead of showing this guy, this fellow, this way it will show in this other direction. These are all various classes of metamaterials which are now finding very interesting applications in engineering. Okay. Now we have measured elastic modulus E, and for an isotropic material, you actually need only two elastic constants to describe its mechanical behavior, that is elastic modulus and Poisson's ratio. If you know elastic modulus and Poisson's ratio, you can also define something called a shear modulus through this relation, G is equal to UE by 2 into 1 plus nu, or other way. Similarly, we can define bulk modulus. What is shear modulus? What is elastic modulus, by the way? Sigma is equal to E times epsilon. That means elastic modulus is normal stress by normal strain. Right? Similarly, shear modulus will be shear stress by shear strain. And bulk modulus will be volumetric stress by volumetric strain. Right? That can be given by E by 3 into 1 minus 2. All right. So for most isotropic materials, we just need two elastic constants to describe its behavior completely. That is E and nu. That is what we will deal with. Any questions until now?
No, sir. Please.
Now we are talking about plastic deformation. So in the when you are drawing the stress strain curve, initially you will have elastic regime. Then we will enter something called a plastic deformation regime, so this is your initial elastic response followed by some nonlinear response where you will have plastic deformation. What do we mean by that? So for many metals, the elastic deformation is only up to a very small strain, 0.005. And if the material is deformed beyond that strain, you will encounter something called a plastic deformation regime. And once you enter the plastic deformation regime, the relation between stress and strain, total stress and total strain, cannot be represented by Hooke's law anymore. Hooke's law does not work. Hooke's law works only in the elastic regime. In plastic deformation regime, as we have discussed, what is happening? In plastic deformation, you have breakage of bonds with the original atom neighbors and reforming bonds with new neighbors. That is what we have seen in the case of dislocation motion. So the original bond will be broken and a new bond will be established with the neighbors. And once a new bond is established with a neighbor, if you remove the stress, the material will not break the new bond and form a bond with the original neighbor. It will remain there. That means the material is not anymore the same material which it has begun to be. So during plastic deformation, the material keeps changing because it is changing its neighbors. So that means they do not return upon removal of the stress, they do not return to their original positions. As opposed to elastic deformation, wherein in this guy, if you are removing the load, it will go back to its original configuration. That means at zero stress, you will have zero strain. The reason for that is none of the bonds are broken. They are only got stretched. Okay. So in crystalline materials, this flash deformation is represented by slip. We have discussed at length. For an amorphous material, it is described by a mechanism called viscous flow because there are no dislocations in amorphous materials, or dislocation like defects cannot be seen in amorphous materials because there is no crystal structure to begin with. And as a result, we have to explain the deformation, flash deformation in amorphous materials by viscous flow. We will not talk about them in this class, but we will only mainly focus on crystalline materials, and the mechanism we already understood to be slip. Slip is nothing but flash deformation by dislocation motion. Okay. So here you have this initial elastic limit, and this point P is what we call proportionality limit, or beyond this point, the material starts getting into plastic range. So we talk about yield strength. So yielding refers to the onset of plastic deformation. Whenever the plastic deformation starts, that is when we say that material started yielding. And we also have something called proportionality limit, which is very difficult to measure. What is this proportionality limit? Proportionality limit says that until proportionality limit, the stress is directly proportional to strain. Sigma can be directly proportional to strain, except that in the proportional limit, they may have some non-linearity. That means sigma is equal to E times epsilon. E may not be constant. U may become non-linear small region, but otherwise it is sigma is still proportional to strain. And yield strength is where the onset of plastic deformation takes place. But if you carefully observe this stress strain curve, you see that after P, which is proportional to point, the material, the line is pretty non-linear, and we really cannot say when did plastic deformation start. Did it start here? Did it start here? Did it start here? Or did it start here? It will be very difficult to find out. So what people have done, ASTM standard says that in the case where you cannot identify the yield point clearly, or even if you identify, ASTM suggested a very reproducible way of finding the yield strength. What they said is, you draw a 0.2% offset strain line. What is the meaning of that? On the x-axis, you know this line, straight line, which is your elastic, slope of this line gives you elastic modulus, linear elastic regime. From there, you look at 0.2% strain. 0.2% is 0.002. So that is this point. At that point, you draw a line parallel to your initial linear elastic regime. That means you are drawing an offset at 0.2% strain, and draw that line and see where that line touches, intersects the stress strain curve, and the value of the stress at which it intersects, that is what you report as yield strength of the material. So in all the design data handbooks, the yield strength of the material is reported like that. You draw the stress strain curve, take the 0.2% offset, and wherever that offset line intersects with the stress strain curve, that is reported as yield strength of the material. In reality, the plastic deformation would have onset somewhere here. But in order for us to have a uniform way of measuring and reporting plastic deformation, ASTM has given this universal guideline so that everyone follows the same thing. Very good, that is fine. But then that is, as long as the material is linear elastic, I have no problem because I can draw an offset line which is parallel to this fellow. What happens if the material is non-linear elastic? That means there is not a single straight line. The curve is to begin with is a non-linear curve. Then I cannot draw a 0.2% offset, right? Then what the prescription is, if the material is non-linearly elastic, then you look at 0.5% strain. Let us say this is your 0.5% strain. Draw a vertical line at 0.5% strain. Vertically up, and then wherever that hits this fellow, that you report as yield strength of the material. These are the two prescriptions, and there is this is only a guideline so as to avoid confusion between different people reporting different values of yield strength of the material. Okay. However, in some materials such as mild steel, one can clearly see the yield point, and this is only true for mild steel, where you can observe an upper yield point and lower yield point. There you need not draw 0.2% offset yield, and you will be able to directly look at it. You can use 0.2% offset yield method when it is not easy for us to identify the yield point accurately like that. Okay. So you can say that the plastic deformation actually starts at the upper yield point, but then you see that suddenly once the plastic deformation started, immediately the stress has dropped, and at that point, at constant stress, very similar to what you have seen in single crystal material, although this is a polycrystalline material, at constant stress you have some significant strain, and of course it is oscillating about that point, and then you have the hardening response. Right? So why this happens? What happens is, in mild steel, you have one of the favorably oriented slip systems reach the maximum yield strength or critical resolved shear stress. That is when yielding happens, because there are so many of them at the same point activated. Suddenly they start deforming, plastically deforming easily, and hence you will have a drop. Here the drop is exaggerated, but in general there will be a drop. And after that, because several slip systems got activated, all of them at the same time, you will have sudden reduction in the stress, because it will be able to deform with much less stress. But then again, there are these small serrations, right? That is what typically observed in the mild steel. These serrations are saying, what is the meaning of this serration? It has normally, unless there is strain hardening, like grain boundary or stopping the dislocations, you should not have this hardening. You should have a straight line like that. But these small oscillations also represent, if you zoom into this fellow, you see that there is a small obstacle, but then the obstacle is overcome. Again, there is a small obstacle. There are so many much small obstacles are encountered by the dislocations. That is why you have these small oscillations. What are these small obstacles? Because it is mild steel. Mild steel is what? Mild steel is a solid solution of mild steel is a solid solution of what?
Iron and carbon.
Sorry? Is an alloy of
Carbon. Iron and carbon.
iron and carbon. You can see that the atom size of carbon is much smaller than the iron. And what happens is, these dislocations are encountering these solute atoms called carbon, very low, small percentage. Whenever they encounter, they see some resistance, but then dislocations are strong enough to overcome the obstacles. That is when it overcomes, then the stress required drops. Again, it will encounter another solute atom. Like that, all these solute atoms are causing these oscillations. And once there are enough dislocations, then your grain boundaries start offering resistance to dislocation motion, and hence you will have this strain hardening that is taking place, or work hardening. Okay. So that means if you take, right, so this is your plastic deformation, and this is what we call strain hardening regime. If you look at a stress strain curve, not for mild steel, for any generic material, you will see something like that. And here is what we call ultimate tensile strength, the maximum stress, and what we are plotting is engineering stress versus engineering strain. If you have a brittle material, you will not see significant plastic deformation. It will directly break. Typically what happens is, you will have the ultimate tensile strength. After that, the engineering stress drops like that, and eventually the material fails here. Right? At this location, you will have something called necking that takes place. That means locally diffuse necking that happens, and as a result, there will be damage that is taking place in the material. Because the material is getting damaged, your force required to cause further deformation reduces, and force per unit area is not changing. Original cross sectional area is not changing, and as a result, because the force is reducing because of the local damage in the material, the engineering stress reduces. Eventually, the cross sectional area becomes so small that it actually causes fracture, and suddenly you have the material suddenly breaking here. A typical ductile material shows this sort of a behavior, whereas a brittle material does not show significant plasticizer deformation, it directly breaks. Okay. So the measures of ductility. So if you have a ductile material, the measure of how do we measure the ductility? The engineering strain at fracture is called a measure of ductility. So that means the fracture, whatever this is the point of fracture, the strain at this point is what is one measure of ductility. And there is also another measure that is called percentage elongation or percentage reduction of area at fracture. So length of the specimen final at the fracture, meaning fracture meaning at this point, what is the length of the specimen before the fracture minus original length will give you percentage elongation or percentage reduction in area, that is A0 minus AF by A0. AF is after the specimen is broken, you can actually measure the cross sectional area. These are the measures of ductility. If you have large values of these numbers, that means you have more ductility to the material. Right? There is another property called resilience. So resilience is the ability of the material to absorb energy within the elastic regime. So you know that if you drop 0.2% offset strain, this is your sigma y. Below the stress, everything is elastic. So area under the stress strain curve, up to that is what we call resilience of the material or modulus of resilience. Strain energy per unit volume required to stress the material from 0 to yield strength of the material. And then we have another property called toughness. Toughness is the ability of the material to absorb energy in plastic range or until fracture. So toughness, how do we measure the toughness? Toughness is basically the area under the total stress strain curve, which means this total area from this to up to this entire area is called toughness of the material. That is reported as toughness. Okay. Now let me go back to my writing pad so that I can discuss few more things in detail now. So now let us look at this fellow. You have a stress strain curve. This is your sigma and this is strain. I am calling it as E because E is engineering strain. Sigma, I am calling sigma E, that is engineering stress. Okay. Now, when I plot the stress strain diagram, that is initial elastic regime, and then you have fracture, and this is my, so if I take, this is my 0.002 strain, then I can right, this will be my what this point
Yield point.
will be my sigma y, yield strength of the material, right? That is how and this point is my sigma ut, ultimate tensile, and this is sigma f, fracture strength. Many times we don't talk about this, we will only talk about ultimate tensile strength. right? But the fracture strength comes later. We are not interested in what happens to the material after this, because once it reaches ultimate tensile strength, the material is already damaging, and hence we are not interested in it anymore. Okay, now let us try to carefully understand this diagram, right? So the slope of this fellow is my elastic modulus, right? Strictly speaking, when you are measuring elastic modulus, what you should do is you should not measure elastic modulus on this line. I will tell you what do I mean by that. Now you have measured yield strength. So now let us imagine a scenario where I have loaded the specimen, and in such a way that I have loaded up to here. That means I am deforming the material, and it has gone up to here. And then I am unloading the specimen. So that means the specimen has become from here. I have extended the length to there, right? And I am applied the load F, right? And it has gone up to here. And suddenly at this instant, I have up to here, I have applied the load, and suddenly I have decided to remove the load. Then what happens? Instantaneously, it will come back to its original configuration. If I do that here, right? Because when you are stretching the bond, so when I am doing this, what is happening is microscopically, I am applying load, right? Then what is happening? These bonds are getting stretched. Right? When I am removing the load, these are going back to this configuration. Is that clear to all of you? And hence, when you are loading in the material in this direction, if I load up to here and suddenly if I remove the load, the material will go back to its original configuration along this path. Why am I saying about that path? Because the bond stiffness did not change. Isn't it? It is only stretched and then removed. So it is. So when it is stretching, it went along this path. When it is unstretching, it is the same bond. The bond has not changed. The neighbors have not changed. Nothing has changed. Because it is the same bond, it has to follow the same path, because that is what is describing the elastic deformation. All of you agree with that?
Yes, sir.
Yes, sir.
So whenever, if the elastic modulus of this material is this, whenever an unloading is happening, unloading is always what? Already, whenever you are doing plastic deformation, some of the bonds are broken and established rebonds. It is not that all the atoms are undergoing plastic deformation, right? Some of them are still under elastic deformation. Can you imagine that? So suppose if you take a material, let us say you have, this is grain 1, grain 2, grain 3, grain 4. Okay, you are applying a load like that. The orientation of this grain is this way, this grain is that way, this grain is that way, and this grain is this way. They have different orientations. Okay. Now, when I'm applying the load, let us say grain 1 is most favorably oriented grain. That means the resolved shear stress on grain 1 reaches critical resolved shear stress before it reaches critical resolved shear stress in 2, 3, and 4. Is that concept clear?
Yes, sir.
Now, when I am applying the load, while grain 1 may be undergoing plastic deformation because the resolved shear stress has become equal to critical resolved shear stress, grain 3 resolved shear stress may be less than the critical resolved shear stress. That means, although grain 3 is not plastically deforming because there is some shear stress in that, some of the bonds are getting stretched. That means this guy may be plastically deforming while grain 2 grain 3 and grain 4 are still elastically deforming. Okay. Now, if I decide to unload the material, that means if I decide to remove the load, what will happen? Whatever plastic deformation that has happened in this, that is taking place, but there may be some, these are all under elastic deformation. So what will happen to their elastic behavior? They will go back to original configuration because the bonds are not broken. And the elastic deformation is described by this bond stiffness. So that did not change. And hence, whenever you are unloading a material, the path should be same as the original elastic deformation path. Which means, if I have loaded a specimen, let us say up to this point, that means I have partially plastically deformed the material. Now, if I am unloading the specimen, the unloading path always should be elastic, because during unloading there cannot be any plastic deformation. All the deformation during unloading should only be elastic, unless it is continued in the unloading direction beyond zero stress. If it is unloaded to zero stress, then you have to unload along that path. And this is the slope of that line should be same as E. Is that clear? If I loaded the specimen up to here, then I have unloaded and it comes to here and then it goes here. So now when I have removed the stress is zero, but is the strain zero?
No, sir.
Although I have removed the external load, the stress has become zero, but the strain is still there. That is what we call plastic strain. This is what we have permanent deformation. The material did not come back to the point O. Material has come back to, say, point P, which has some residual strain. That is what we call plastic deformation or plastic strain. And carefully observe, when it is loaded up to this point, from say this point A, from point A it is unloaded, then it went to point P on this graph, having a plastic strain of some value. But initially at point A, this is I say A bottom. That is the strain, right? At this point is represented by, say, let us say, strain at point corresponding to point A, sigma at point A. This is my strain at point A. Right? That is the stress state of strain. But when I have unloaded, this is EP. Meaning, during unloading, this much strain is recovered. That is what we call elastic recovery, elastic strain. That much of elastic, that means so much of elastic deformation is there in the total deformation. So the total strain EA can be written as elastic strain plus plastic strain. And this is my elastic strain. All right. So depending upon the level of strain that up to which you are loaded, your elastic strain and plastic strain components will change. Okay, because this curve is non-linear. Depending on the nature of this curve, you will have different elastic and plastic strains at each and every point. Now, in the experiments, when you are measuring elastic modulus, the good way to measure elastic modulus is not to use this fellow, but use this fellow, the slope of this line, because unloading path is purely elastic. And hence, it is better to load the specimen up to some value and then unload it, measure the slope of that line, that will be your elastic property. So that will be your elastic modulus. Is that point clear?
Yes, sir.
Any questions here? Okay. Now, let us try to understand a little bit more detail here. Now, I have taken a specimen. So now let me draw this picture again for you. Another stress strain diagram. Engineering stress, engineering strain, and the stress strain diagram is this is my sigma ut and whatever sigma y I can always measure. You know how to measure sigma y, right? Are you able to see my screen?
Yes, sir.
Yes, sir.
Yeah. You can measure sigma y by 0.2% offset yield. Fine. Now, let us say I have a scenario wherein I have loaded the specimen up to here. So let us say this is my sigma y of the material. Okay. I have loaded the specimen beyond yield strength of the material, and then I have unloaded this fellow. Okay. I have unloaded. So I have taken a specimen, loaded the specimen and unloaded and kept the specimen. Now if I take that specimen, so you have started with this specimen, loaded. So this is 0.0, let us say 0.1, and this is 0.2. At 0.0, that is like this. You have the specimen, and 0.1, it has become like that. And when you have unloaded, it will not be coming back to its original configuration. It will somewhere in between, right? That is the status at 0.2. Is that clear?
Yes, sir.
Yes, sir.
No. Now it is unloaded. Now you can take this specimen. Now, if I take this specimen and do the tensile test again, okay, then what happens? Then what will be the so if I do the tensile test again, what will be the yield strength that I will measure?
Point to offset from the green line.
So let us say corresponding to this, that is sigma 1. Okay. Now, if I take specimen 2, I do a fresh uniaxial tension test. Okay, because I have unloaded it. Now it is as if it's a virgin specimen. I have unloaded it. And now I take the uniaxial tension test. When I do the uniaxial tension test on that specimen, let us say that is done with, I'm drawing it with the blue curve. How does the stress strain response look like? Will I measure the yield strength when I am doing the test on specimen 2, which is same material, right? The material did not change. Just that specimen has been deformed and then deformed specimen I am checking. Whether the specimen 2's yield strength will be same as the yield strength that I have measured originally, or specimen 2 yield strength is less than sigma y, or sigma y specimen 2 thing will be greater than sigma y. What is your
Will be
assessment?
less than sigma.
It will be less than sigma y. So let me draw this picture. So will it be initially elastic or not? Sorry, it will be initially straight line or non-linear line?
Straight.
Linear. It's
Hmm?
linear.
linear. So it should be like that.
Yes, sir.
Where will it start becoming plastic? You said it is below that, right? Like that?
Sir, does the blue line starts at 2 instead of 0?
Okay. When I am doing a fresh test,
Okay, got it.
yeah. So, okay, let us say I am doing a fresh test. So I am to avoid that confusion, all that I can do is I can draw my origin can be this now. Okay. If my origin is this, okay, now I am starting here, it is 0. Now tell me how the curve should look like.
Sir, it should follow this green line from 2 to 1.
It should follow the green line up to what?
But somehow as
Up
up to
to
point 1.
sigma y, up to here,
Up to sigma 1, sir.
or up to sigma 1.
Up to sigma 1.
Why?
Because that is what is now your elastic.
Exactly. Because there you have unloaded, from there you have unloaded. So until you reach sigma 1, you will not initiate plastic deformation. At sigma 1, again it starts following the same path. Right? So the yield strength that you would measure for specimen 2 will be equal to sigma 1, which is greater than sigma y. Which basically means that when you are doing the strain hardening, this is what we call hardening, right? Hardening method. Hardening means it is harder to plastically deform the material. That is the reason why at this point the yield strength will be higher than the yield strength here. Which means as you are deforming a material, for example, you have taken the specimen and let us say different points you are taking the specimens. So let us say A, B, C, D, E, and this is this is 0, A, B, C, D, E. All of them will have same elastic modulus, but same E, but different sigma y. That means the material during plastic deformation, what you are doing is you are creating new material at each and every strain. As you are traversing on this red line, on this path, you are actually creating new material with each and every small increment in the strain. Because the new, why am I calling it as a new material? Because the yield strength of the material is changing. That is what we call strain hardening, because it is becoming harder for the material to get deformed. Okay? Any questions here? This is a very important concept to understand about your plastic deformation. Okay? Now, in the uniaxial tension test. Now, let us look at again. We continue.
But this might be different for a material like aluminum. Is that right?
No. Why would it be different for aluminum?
Because we don't have a specific yield point. I mean,
No,
we
here
just
also
stuff
there is
the-
no specific yield point. No, in this graph, where is the yield point? 0.2% offset only, no?
Yeah, right.
Yeah, this is my yield point, right?
Right. Yeah.
It is actually for material which does not have specific yield point. Any material, once it goes beyond yield point, when you unload it, its yield strength will be more than what it was to begin with. Okay?
Okay.
Yeah. Now, we said engineering stress is equal to force load by original cross-sectional area, right? Now, true stress is defined as, so this is sigma E, and now I am calling it as true stress as sigma T, P by instantaneous cross-sectional area or current cross-sectional area. A0 is original cross-sectional area. Instantaneous cross-sectional area. Now, we also have defined engineering strain as LF by L0 minus 1, correct? Or final length, my original length. And true strain is equal to, or the current length minus volt. True strain is given by natural log Li by L0. AI is instantaneous, or that instantaneous could be in the final end. Right? Now, what happens is, when the material is plastically deforming, right? What is happening is, it is only changing its shape. And there is no volume change. Meaning, you have A0 L0 is equal to AI Li. Okay, there is no volume change, means this is what should happen. Now, we know engineering a true stress is equal to P by AI. That can be written as P by A0 times A0 by AI. Can I do that? And now I can write A0 by AI is equal to Li by L0. So that is equal to P by A0 into Li by L0. So P by A0 is what? Engineering stress times Li by L0. That is your true stress. What we have learned here, true strain is equal to natural log Li by L0. So this implies natural log right, epsilon T is equal to 1 plus this thing. So this Li by L0, can I write sigma E into
1 plus E.
you look at this fellow. 1 plus E, that is engineering strain. So now you have these two relations. That means your engineering stress is equal to Le 1 plus E, that is relation between engineering components. True is natural log 1 plus. Okay. Now, in this stress strain curve, let us look at the stress strain curve once again. Stress SS strain, sigma T, sigma E, engineering stress versus engineering strain. Okay. Now, if this is how your typical engineering stress strain curve look like. Now, if you look at the true stress strain curve, what is happening here? Before necking and after the plaster deformation. This is onset of necking, right? So this can be represented by a functional relation, that is a power law relation, sigma t is equal to k epsilon t power n. It's a one of the from onset of Flash deformation to here. Let us say this is where Flash deformation is starting, and this region can be represented by this fellow, where k is called strength coefficient and n is called strain hardening exponent. So it basically tells you how the strain hardening taking place. It can be a non-linear response up to onset of necking. So what do you mean by necking? Locally up to here, you will have some gauge section like that. Then the necking happens locally, there will be damage. So that means there will be highly localized deformation, and eventually there will be a breakage happening. So that we will not consider. Up to necking is what we are looking for. Okay. So the relationships, because when you are doing when the necking begins, then there will be a local volume change. So constancy of volume cannot be applied. So the constants, these two relations are obtained based on volume constants. So we have written, so this within this regime only you can apply sigma t is equal to sigma e into 1 plus e, epsilon t is equal to natural log 1 plus e. These can be applied only within this regime. Okay. Because after that volume constancy does not work. And now you can so now if you would plot the true stress strain curve on this graph, how does it look like? The true stress strain curve. You can see the true stress strain curve is nothing but load by instantaneous cross sectional area. So when you look at up to necking, after necking, what happens to cross sectional area?
It will reduce.
Reduce drastically.
So that means drastically reduces. That means sigma t should increase. So it should not be decreasing like that. The curve should be going like that, isn't it? True stress strain curve.
Yeah.
Okay. And then if you look at the true stress strain curve, the value of the true stress strain curve will be greater than engineering stress, isn't it? Because it's 1 plus e. It cannot be same as sigma e. So that means in this regime, this should be larger than. So that is how the true stress strain curve should look like, isn't it? Because this is always greater than this one. For the same E if you are plotting. And usually let us say this is the onset of necking, and the onset of necking is trailed in the engineering true stress strain curve at m dash. You can actually verify by looking at the values of epsilon t corresponding to that, because you are plotting sigma t versus epsilon t true strain. Okay, so a true stress strain curve will not show a maximum. It will continue to increase in a material. Okay. So now we have seen the relationships here, and now let us look at the necking. Let us try to understand what is happening in necking. So necking, as we understand, it's instability, and it onsets at the maximum engineering stress value. That means whenever the load reaches a maximum value. If you would draw the stress strain curve of force displacement response, no, P versus delta, you will have some increase in force and then suddenly decreases. Wherever P is maximum, that is when necking begins, right? Or in other words, like this, you will have a maximum value of P, which is nothing but, it is nothing but d sigma engineering stress by d epsilon engineering stress should have maximum zero value, isn't it? Because that is where it is reaching maximum value. That is where the slope should be zero, isn't it? Which is nothing but dP must be equal to zero. That means because there is no change in force at that point. Otherwise, the change in force will be either positive or negative, whether you are on this side or that side. Now, the force, applied force, is equal to, you can write engineering stress divided by original cross-sectional area. Sorry, engineering stress into original cross-sectional area, or this can also be written as true stress into current cross-sectional area. Can you do that? Is that clear?
Yeah, both are one and the same.
One and the same. So now then, if you talk about variation in P, you can write, if you look at this fellow, as P is changing, sigma T changes or not? As P changes, sigma T changes or not?
Yes,
Yes.
As P
it
changes,
changes.
area changes or not?
It does.
Also changing.
It
So
is.
I can write this, I can apply chain rule. I can call this as sigma T dA plus d sigma T A. Right? That must be equal to 0. And we had from volume constancy, just before the onset of necking, we have volume constancy, which basically tells us that dL by L is equal to minus dA by A, because increase in length should be compensated by reduction in area. And hence, dL by L must be equal to minus dA by A. dL by L is equal to d epsilon true strain. Right? So, what you can show now, d sigma T by d epsilon T is equal to, so now if you look at this equation, sigma T dA plus d sigma T A equal to 0. That implies d sigma T by sigma T is equal to minus dA by A. Can you see that?
Yes, sir.
Is that clear? D sigma T by sigma T is equal to minus dA by A. All right?
Yeah.
So minus dA by dA is nothing but d epsilon T. So that implies d sigma T by d epsilon T is equal to sigma T. That is at the onset of necking. Can you see that? Which means, when does necking happen? Necking happens when the derivative of sigma true stress with respect to true strain becomes equal to the value of true stress. So the condition for onset of necking can be d sigma E by d E equal to 0, or d sigma T by d epsilon T is equal to sigma T. Both represents condition for necking. Now, if your from here to here, if the power law is representing, if sigma T is equal to K epsilon T power n, if that is the response until the onset of necking, then I can write d sigma t by d epsilon t is equal to k n epsilon t power n minus 1. Right? But at onset of necking, d sigma t by d epsilon t, which is equal to k n epsilon t power n minus 1 is equal to sigma t. That implies k n epsilon t power n minus 1 is equal to sigma t. Sigma t is again k epsilon power n. K gets cancelled, and that is equal to n by epsilon t is equal to n by epsilon t times epsilon t power n is equal to epsilon t power n. This is cancelled. That implies epsilon t is equal to n. If it is a power law, a hardening response, then at onset of necking, the true strain becomes equal to strain hardening exponent if it is represented by this relation. If it is some other relation, then we cannot say. But if it is a power law relation like that, then at the onset of necking, the strain hardening exponent becomes equal to the true strain. That is when necking begins. Okay. So this conditions, for the condition for onset of necking is d sigma e by d e is equal to 0 or d sigma t by d epsilon t is equal to sigma t or epsilon t is equal to n if sigma t is equal to k epsilon t power n. These are all equivalent conditions for onset of necking. So if you are having a true stress strain curve, you don't have an engineering stress strain curve. If you have engineering stress strain curve, you can clearly see when the necking happens, when the slope is 0. The meaning when the maximum point is there. But when you have true stress strain curve, you cannot see where the necking begins because there is no maximum point. Then all that you can do is you can compute derivative of sigma t with respect to epsilon t, and then whichever value of that corresponds to sigma t value itself, then you say that that is the point at which necking begins. Okay? And this is what we call considerous criteria for onset of necking. That is how you will find out when the necking begins in a material. Okay? So in this class, what we have learned, yeah, any questions? No. So in this class, we have learned all about the tension test and the uniaxial tension test curve, followed by measurement of the mechanical properties and how do you characterize necking in a plastically deforming material, and other properties like resilience, toughness, elastic modulus, yield strength, how to measure them given a tension test data, stress strain data, and how do you compare how do you write the relationship between engineering quantities and true quantities. This is all we have learned in this class, and from using this as a basis, we will start talking about failure theories in the next week onwards. From the next week onwards, and I will post an assignment in the Google Drive sometime this week so that you can start working on the assignment. Okay? If you have any questions, I'll be happy to take. Otherwise, we'll close the session today. I have uploaded the mechanical properties lecture notes already in the Google Drive.
Professor, your handwritten notes also, could you please upload?
Yeah, I will try to upload this also. 1 minute. Yeah, I will do that.
Sure, thank you, sir.
Thank you so much, sir.
Okay, bye.
Thanks, Professor.
Thank you, sir.
Sir,
Thank
only
you.
one request.
Yeah.
I was present in the class yesterday, but somehow I think I didn't post my attendance. So
That's okay. We'll take care of that.
sure, sir. Thanks a lot, sir.
Yeah.
Thank you, sir.
Okay, bye.
Bye bye.